Okay, so now I'm at module 4, and this is totally on the discussion of loads and boundary conditions, and this will cover the project 2. I already have opened the project 2 file that is visible here, and let's say we have these parts modules here, parts classification here. It is a multi-layered system, and my main focus in this lecture is discussion on the definition of the loads in pavement analysis, and the other thing is to use Python to visualize the loading effect contact patch area of the tire, and also I need to demonstrate these codes in this module 4. Then I have discussion on this dynamic versus static loading, and I have a detailed classification of loading amplitudes and Python codes which covers the traffic load modeling with cyclic amplitudes, and other than that I have this thermal and environmental load consideration here. I will be discussing in this module in detail. I have this Python code to generate the sinusoidal amplitude, which is very important, especially if you are working with ABAQUS. And also I have this step amplitude, which we mostly consider for snow loads and contact pressure loads. And I have a special design criteria for that snow load for the time period over an year. So that's also something which is very important when you are working with your flexible pavement projects. Then I have this RAM for linear amplitude, which is for gradual changes in load and temperature. So I also have considered throughout the year value here, and after that I have a custom amplitude for any arbitrary load or temperature variation. This is also for whole year, you can see here, and I will demonstrate all these values. Other than that, I have this bonus code which bypass Microsoft Excel due to limitation on the row counts. It's very common problem. Maybe it will be a new thing for you, but when you are working with Python, you actually encounter this error of maximum limit of rows in ABAQUS. So in Microsoft Excel. So this is also important. So it bypass that problem, and it's automatically create an input file for you. So if you look at the code here, it actually convert this text file to input file, and I will demonstrate this also. Then after that I have a detailed discussion on applying boundary conditions. So I have this this model, so I will discuss that, and after that we mostly face two problems, which most of the time if you are watching any kind of videos, they do not explicitly mention it. The first one is the pavement edge modeling in ABAQUS, and the second one is the boundary value issues and ABAQUS. So these two are the things that you need to consider when you are working with your ABAQUS models. So let me quickly show you the bonus code which I mentioned here, that it is going to bypass the problem of Microsoft Excel. It's a very best code, and let me just show you that. It is present here. So let me just delete these. Right, this is the main code which will create input file for us and bypass Microsoft Excel operation, and then we will discuss something about tire contact area as well, and also I think I have this how to transfer amplitude. This is a new new aspect you will learn in ABAQUS. It is related to I think it's related to copy objects. So if you have more than one model, you can do that. And since I'm using this code here, this is generating input file for me. So I will need this code, and I will need that discussion here. So it is related to copying objects between two ABAQUS files, ABAQUS modeling environment, right? And this will be a research paper that I am going to discuss, in which there is a detailed discussion on tire patch area, their testing procedure. That is actually a dual tire cart, right? So just in case if you are working with your ABAQUS files, you will be able to do technical discussion on it. I also have this discussion in this module 4, manipulating models within model database, and this thing is very interesting here, which you will also learn. And let me show you. For example, if I copy these codes, these results that I already have generated with Python code, and I place them here. So by double click on it, I am actually generating input files for myself, right? So the input files are generated, and I can quickly import them to use in my own study. So you will also understand the significance of using Python, right? And you will be able to work on any kind of course that you are using here. So right now you actually saw this activity that I generated the input files, and those input files are present here. So if I click on it, this input file, this is imported into ABAQUS, and now that amplitude which I generated actually is present with me, right? So that amplitude is here. So this is something that I generated with Python, and I bypassed the Microsoft Excel, which is a good thing if you are working with any kind of files. You will be able to do that. So let me show you what actually is it. So it's actually this Python code from sinusoidal amplitude, and for every minute it's giving me these values which I'm going to discuss. Now it's very difficult to just work with it and then generate these files and copy them to Excel. And there is a big problem if this exceeds the number of rows of Excel and you have a larger time period. You will not be able to use it in ABAQUS. The reason is it will give you an error. Python will not be able to use it in Excel due to limitation of the row size, which sometimes occurs, and for that you need to actually bypass the files that you are using. So there is a lot of discussion in this module 4 which is going to take place. Also, as I mentioned, we are going to develop that amplitude. For example, I have this amplitude right now, and if I want to copy this amplitude and to this environment, for example, in multi-layer system file, a modeling environment, I have these amplitudes that I am using right now here. And let's suppose I import them into a multi-layer system file. So let's say I want the other amplitude to use it, which I generated in Python. So I will select the object to copy. So from this input file, this is the input file that I generated actually. I am going to take this amplitude and I need to use this in multi-layer system modeling environment, which is actually this model of flexible pavement. So as soon as I select it, you need to focus here. When I click on apply, that will appear here. So you can see here that appeared here by just clicking on apply here. So I quickly generated this. So this is something interesting which I did with this Python code, and I wrote this code with ChatGPT. Actually, I trained ChatGPT to write a code for me which create input file for me, and it's not a difficult thing to do. Just you need to have an engineering judgment which can be quite tricky for you, right? So this is the backbone of this whole code, and also this is the backbone of this whole code. So these are the two ideas that actually came in my mind when I was working with these codes. So I thought if I am doing it with Microsoft Excel sheet, which actually I did, and I faced problem in it. So it's very important to you just focus on these, because if you are actually interested in just quickly doing things without understanding the process, you may be able to understand one project, but you will not be able to understand the whole process. So this why I'm not just repeating this multi-layer system, because when the course is completed, at the end I will try my best to create one model which will cover the whole process. And actually I'm trying to make it more interesting by including a lot of other discussion on this project. So that's why it is more than a practical course. There is a lot of technical discussion, a lot of Python codes. So if you are able to focus your attention on this, you will be able to understand. Otherwise, if you are just a spoon feeding baby and you only follow the procedure, you will not be able to understand it, because I'm not doing it in that fashion, right? So it's a complete discussion. At the end, when I feel that now it's a time for it, then I can do that. Definitely I will do that. At the end, I will try to generate some models and work on those models. So there will be a lot of discussion in that regard. But right now, I think it's okay to just continue in this manner. So in module 4, I mentioned the loads and boundary conditions, and the first thing that you need to consider is if you are defining the loads and boundary condition in your ABAQUS file, actually you have to understand that for every model the boundary conditions that you are using, those will be different, right? Every time you are working with your model, you will be using different loads and boundary conditions in your ABAQUS environment. So in ABAQUS, with understanding the boundary conditions under different scenarios, it will help you to simulate the real world problems by just applying forces, pressure or constraint to the model. And these are actually the loads and boundary conditions. So loads are actually external effects, while other than that the boundary conditions are the regions which are taking into equilibrium when you are working with the model. So the loads may be forces there, those may be weight and temperature, etc., whatever those are, and the boundary conditions are those regions which you are applying to fix them. So actually these loads and boundary conditions is making sense in interaction with the environment, and it can vary over time or space, right? So that's why if it's vary over time or space, you need two positions. With time, you need time series to consider that, while with space, you need to consider geometry, right? So that's why the amplitudes and all those steps are important in your model. Boundary conditions, on the other hand, are used to fix or constrain certain parts of the model. For example, if you want to keep a section stationary, right? So you want to limit some movement in a specific direction, so to prevent unrealistic behavior, you do that by applying those boundary conditions. So in ABAQUS, if you are applying the right loading and boundary condition, it is very important for obtaining the accurate and reliable results. And that's why in order to discuss this, the loads and pavements are revolving around the tire patch contact area, right? And the tire patch contact area, when you are working with finite element modeling in ABAQUS for flexible pavement analysis, the modeling of the tire patch, which is actually the contact area between the tire and pavement, is accurately important for several reasons. So if you need, as I mentioned, if you need realistic loads distribution, the tire pavement contact area works for you. It's actually determined how the vehicle load is distributed across the pavement layer, right? So that is important. Other than that, it's also important to consider that region in your model. For example, I am defining a specific load, a tire contact area for this region. Then I have a tire contact area for this region and this region and so on. So it's important if you need the realistic load distribution, you actually need the tire pavement contact area to determine how the vehicle load is distributed across the pavement layers. In the previous model, I also adopted this similar methodology. So also that tire patch, which actually I have considered here, this tire patch is important to model. So if you have a poorly modeled tire patch and assuming a point load or a uniform pressure without knowing the reason behind selection, so it can overestimate the localized stresses at these regions. and it leads to unrealistic predictions of pavement damage. So if rutting and cracking is occurring, those unrealistic behavior will be dominant here. So flexible pavement, as I mentioned, those are layered system. For example, if you have asphalt base and subgrade, and the shape and the size of the tire patch actually directly affect the multi-layer system to these layers. So if you have the tire patch just like this, look at this dual tire load cart here. So it may overestimate the results if you did not properly define it, because the lesser the tire patch, the more concentrated stresses will be dominant, and vice versa. The second reason is the stress and strain accuracy. So stresses in pavement layers are highly sensitive to the contact pressure distribution, right? So the real tire actually exert non-uniform pressure, and it is higher at edges due to tire stiffness, which create a complex 3D stress state, and a simplified uniform pressure assumption can underestimate the critical strain in the asphalt or subgrade. So actually a film requires precise input for the tire patch geometry. It may be elliptical or rectangular shape, and pressure profile to capture the gradients accurately. Look at here, so, right? So if it is rectangular, it means the tire patch will be somewhat circular in region, elliptical in region. If it is square, it will be a circular region. Also, the axle also have impact on it, right? So if the axle is not accurate, this imperfection will cause a lot of problem for you. And this is the other explanation for it. If the input of the tire geometry is not correct, it will create some local problem for you. This region, this has no dominant accurate tire contact region, so the tire pressure is less and the tire contact area is more, so the load is distributing in more region, so its impact is less as compared to this one. So it's also important the friction is dominant in it. And the third one is the dynamic and moving load effect. So for example, if you are performing a dynamic analysis, so the tire pavement interaction affect vibrations and its fatigue and permanent deformation. And I have discussed that effect as well in the previous lectures. Other than that, the transient nature of the contact area. For example, if we are considering an uneven surface here and you are considering the imperfection in the model. So in uneven surface, the acceleration and braking introduce shear stresses and horizontal forces, which are very important for modeling rutting or showing failure, and those are critical here. So the ABAQUS use contact algorithm to simulate these interactions, and the tire patch definition ensure proper force transfer here, right? Just in case if you are defining the interaction, let's suppose I don't have any interaction, I am tying them here, right? Look at here, interlayer interaction. So we have this normal behavior and tangential behavior. So this is very important. Other than that, the failure mode prediction. So for example, the size and pressure of the tire patch influence failure mechanism. So the smaller patches, the higher contact pressure, increase surface layer stresses and accelerate the top-down cracking. And larger patches reduce surface stresses, I mentioned, but it amplifies strain in deeper layers. The concentration become more dominant. So it leads to rutting. So if the patch is smaller, actually the top-down cracking will be dominant. But if the patch is larger, rutting will be dominant. So dual tire versus single tire also produce stress distribution in a different manner. You can see here, and it's also a dominant. So these are some of the factors that you need to consider when you are working with the tire patches. And then mesh sensitivity is very important aspect you need to consider. So a coarser mesh near the contact area may miss stresses concentration, while an overlay defined mesh increase the computational cost. So I think properly defining the tire patch ensure a balanced mesh that capture the critical stress strain, field output, and overspending without overspending the resources. So these are very important, and I think the real world pavement testing, if you are working with experimental data, you need to be careful about it. So in ABAQUS, if you are working with ABAQUS, you need to define the tire pitch as a pressure distribution. So it may be parabolic or trapezoidal over a rectangular elliptical area. So you can also use analytical rigid surfaces or deformable tile model to simulate contact if you are working with it. I will try to do that. And you can also apply dynamic loading or rolling condition to mimic mowing loads, which I will also try to show in some of these projects. And make sure why it's easy to get wrong. This is very important and funny. Ignoring the tire pad geometry or pressure distribution can also lead to underestimating the fatigue life sometime if you are working with fatigue. And overlooking shear failure in asphalt layer also has incorrect rutting prediction in this upgrade. So it's very important to consider these accurately. And you need to make sure that FEM reflects the real world pavement. That's what the effort you are doing for. So these are important. You need to consider the tire patch in such a manner that if you are working with the tire patch, you have a clear understanding of why tire patches are important in your ABAQUS model. So in the next lecture, I will discuss these distributions of the tire patches, and then I will demonstrate them with Python code as well, right? So then you will be able to understand what I'm trying to convey. And then when you are trying to create some sort of tire patches, you will be able to understand which tire patch is important and which is not important. So make sure you understand this whole process and you have no difficulty in working with finite element analysis model if you are working with flexible pavements. So stay tuned. In the next video, I'll try to discuss these equations and the modeling of these equations with practical demonstration and graphical interpretation. And I will also then try to discuss them in ABAQUS by demonstrating them. So thank you so much for watching.